So far you've used the concept of torque in problems where nothing was accelerating. So we were using the rotational version of Newton's second law. Sigma torque equals moment of inertia times alpha, but alpha was always 0. The pinnacle of rotation problems are rotational dynamics, when you have things that are both accelerating and spinning and changing their acceleration. These can scare students off, but the important thing to remember is it's just the exact same thing we've always done for forces. We just have to have a really good picture, and we have to take into account distance from axes of rotation. So I wanted to look at something called the Atwood machine. The Atwood machine has a mass on one side and mass on the other, and they're unequal, so there's an acceleration being caused. We're going to assume that mass 1 is greater than mass 2, and that means that we're going to have an acceleration in this direction, and that's going to cause an angular acceleration like that. So up until now, we've looked at pulleys as being these perfect things that simply change the direction of an axis. So we could do sigma f equations, and we would flip the positive direction as we go around the pulley. But in reality, pulleys are not perfect. Here's a pulley. To get it moving, I have to apply a torque. And there's clearly a torque on it because it doesn't stay in motion forever. So we have to consider the rotational inertia of this. In this problem, we're going to ignore the torque caused by friction, but we are not going to ignore the fact that this pulley has mass, and it's going to resist acceleration, just like these masses do. How do you solve the problem? It's pretty straightforward, and we're going to do one together. But as before, we could write sigma f equals ma for this block. We could write sigma f equals ma for that block. And we would do that merely by putting our forces on. We'll call that ft2. We'll call that fg2. We'll call that ft1. FG1. And before, FT1 and FT2 would have been equal. We could cancel things out. That's not going to be the case now, because the pulley, its resisting motion, is going to make these two forces unequal. So it's almost like we have more unknowns. But we also have one more equation. And the new equation would be sigma tau equals I alpha. So we're going to use these three equations, the sigma f equals ma for this block, the sigma f equals ma for this block, and the sigma tau equals I alpha for the pulley, in order to solve this problem. We're going to figure out about this acceleration. We have to, of course, keep in mind that with torque, the distance from the axis of rotation is important, so we'll have to measure this radius. So let's do an experiment where we take all of these into account. We actually could get a really surprising result from the experiment, a measurement for the value of the acceleration of gravity. Let's take a look. The Atwood machine nowadays in physics class is mostly used for an experiment to measure the acceleration of gravity. If we can get the acceleration of the two masses, and we know what the two masses are, we should be able to take that acceleration, plug in to free body diagrams and sum of force equations, and end up with a measurement of g, basically. So before I had students do this, I did a sum of force and sum of torque equation. And you'll see these on the next slide. So we can look at them in more detail then. But I just wanted to make sure you knew what experiment we were doing. We're using the Vernier LabQuest in order to get the data for acceleration that we need. And it's set up so that the pulley is inside a photo gate. And if you look, you can see a purple light. And that's an LED that is shining across this gap here. And as the pulley turns, it blocks and unblocks that. And the LabQuest can actually interpret that on how fast the rope is moving in the pulley. What's kind of interesting is that you watching this video can see that purple light, but I can't. It's actually an infrared LED, and phone cameras are sensitive to that. The CCD chip picks up that wavelength of light, but our eyes cannot. So it's kind of like the one in your remote control. So anyway, to do this experiment, what we're going to do is we're going to put the LabQuest into graphing mode. And right now we've got two hanging 50-gram masses. What we're going to do is put one of the extra weights. I have a 5, a 10, and a 20. And in class, students did all three. Today we're just going to do the 10. I'm going to load that on one of my sides. And after that, it should be ready to go. I just need to tell the LabQuest to start measuring. So we just hit play, and it will wait for motion, and then we just set everything in motion. And essentially just drop them. One rises, the other falls. And that'll get our data. So here's our data. We've got a parabolic distance time graph on top and a linear velocity time graph on the bottom. And the slope of that velocity time graph will be the acceleration we want. So we need to select the data we want, and that'll be everything before the hit. So that should be a good region of the graph right there to get it on. And then we're going to go to Analyze, Curve Fit, Velocity, and we want linear. So there's our data. We have an acceleration of 0.827, and that's what we're going to use to plug into our calculations and hopefully get little g. So I said we could use the Atwood machine to get a value for the gravitational field, little g. I want to show you how you do that. You should study this slide here, and all it does is it goes off this free body diagram and uses the net force equation sigma F equals ma for each block, and then the net torque equation for the pulley. Back when we were talking about ideal pulleys, we also used a sigma F equals ma equation for the whole system, but that doesn't make as much sense here because nothing's going to cancel, since when the pulley's mass is important, Ft1 and Ft2 don't end up being the same thing. So if we look at our three equations, we have sigma F equals ma for the M1. Notice that we have to be very careful with our axes here. Just like before, the pulley will change the direction. So positive x on this side flips to positive x down on this side. We also have to consider the direction of angular acceleration too. So if this block's accelerating up, this one's accelerating down, that means the pulley is accelerating counterclockwise. So I've called counterclockwise positive. So if we look at sigma F equals ma, Fg on the left block is positive, Ft on the right block is positive. In addition, the torque that block 1 causes will make a counterclockwise rotation. The torque that block 2 causes will make a clockwise one. So the torque of T1 positive. You then plug in everything you can. We have equations for Fg. And we have to remember torque is the lever arm times the force. We also have this last thing where alpha equals A over R, and that's from the rotating without slipping condition, A equals R alpha. Once you have this, you've now got three equations, and you could solve the two force equations for Ft1 and Ft2, and you could plug in. The math becomes pretty ugly, but you just keep going step by step. And you actually have a lot of these numbers because you know the masses on each side. We measured the circumference of the pulley by wrapping a string around it, and we just used the circumference equation 2 pi r to solve for the pulley's radius. Our pulley also came with its moment of inertia known. So the lab quest gave us that the acceleration was 0.827. So we could plug in, the only thing not known here is actually little g. Now we could say it's 9.8, but these numbers won't work out exactly in that case because everything else is something we measured perfectly. So we should see if little g actually is close to 9.8. So we plug in all the numbers up here. We solve and we get 9.26, which is a pretty close number to what the accepted value is and more accurate than anything we've seen so far this year. So this is obviously in the album. You can study it, and I just want you to not be scared of dynamics equations. They're not that bad. You just have to remember to also write your torque equation and make sure your accelerations are consistent between all three, and sub in for alpha so that it has a in it as well. Here's another dynamics problem that's in the album. I got excited by a problem in Survey and Jewett involving a tire rolling, and I thought I'd make my own. It's very complex looking, but there's a couple big ideas I want you to understand. So please do check this out in the album. Basically says a tire rolls down a ramp, and it wants a time it takes in order to do that, basically. So we put our forces on there. We're careful to draw where they're acting from, Fg from the center, force of friction from the rim. We've got our sigma Fx equals ma, our sigma Fy equals ma, and our sigma torque equals I alpha. So the bulk of this problem is actually calculating I. And that would take a lot of time. So I just think it's worth looking at to make sure you understand how it's done. In this case, Survey and Jewett model a tire as being two sidewalls and a tread wall. And basically they find the moment of inertia of all of those pieces. So they treat them as several different disks with different depths. So here's the calculation for moment of inertia for one depth. And then you do it for the sidewalls, you do it for the tread walls. And then the key thing is you add all this together. The moment of inertia of a complex object, this is something I think is worth remembering. You just add the different moments of inertia together. Once all that work is done, then you just plug into your torque equation and your force equations, and you get an acceleration. Remember, you relate angular acceleration to regular acceleration using A equals R alpha. So, another one worth studying. I don't think you'd have to do a complicated calculation like that on any sort of test, but drawing the three equations, knowing that moments of inertia add together, and then solving for an acceleration and combining it with kinematics equations, that would be something that you should know how to do. Again, don't be scared by these rotational dynamics problems. It's the same stuff we've always done with force equations. You just have to remember this last one here too. So here's another problem. And in the previous problems, we had a bunch of information about force, and we were going to use forces to find an acceleration, which then we could go on and calculate other stuff with. In this problem, it's asking us to compare a meter stick when it's being held like this, pinned here, and then let go. So we're also comparing that with the meter stick when it's fallen down. Two different locations. So forces are not the best way to solve for
how something changes its behavior in two locations, energy is. That was true for linear motion. It's true for rotational as well. So we use that same toolbox idea. What's the best tool for the job? And we see that EO equals EF is a better choice than forces. The same choices apply for rotational motion. All I've done here is I've put in the energies before, the energies after. I had potential before and after. I moved the potential before over to the other side just to show that it's really the difference in height between the center of mass before and after that's going to tell us about potential energy. Kinetic energy uses the new kinetic energy equation we have for rotational motion. And it becomes just as easy to solve as any other EO equals EF equation. Possibly the one trick here is we need to get the moment of inertia. So we use the same integral we've seen many times for a roughly one-dimensional object. The limits change because of where we're pinning it. But we take that integral and we end up with a value for moment of inertia. And once we have that, we can just plug into our energy equation and we end up with a value for omega. Since it asked about the tip of the stick, we use V equals R omega with the whole length of the stick as R. We get our answer. I know this looks different, but it's just another conservation of energy equation. Just like the other ones were all just force equations.